This assessment asks us to treat the same alkene under two different sets of electrophilic addition conditions. In addition to predicting the product of these reactions, what we're really going to learn from this is how the different conditions change the outcome. And so I've gone ahead and shown the first step of each. When this alkene grabs a proton, we make a secondary carbocation. Now you'll note that this secondary carbocation is next door to a quaternary carbon. Anytime we have a carbocation that is less substituted than a neighbor, a rearrangement can occur. So we can show a methyl shift to go from that secondary carbocation to a tertiary carbocation. Let's look at the bottom example. When the pi bond attacks mercury, mercury using its d electrons automatically attacks back to give us this mercurinium ion in a concerted step. The carbocation never forms, this molecule cannot rearrange. And so already, before we've even drawn the products, we see why these products are going to be different. Up here, rearrangement can occur. With oxymercuration, rearrangement cannot. Let's see how this reaction finishes. Water is going to attack and open the mercurinium ion at the most substituted carbon. When it does, it brings along its proton. Having brought along its proton, another molecule of water can remove the acidic proton so that we finish with this alcohol. Now the mercury is still attached. There's usually going to be a step 2 to this process, and that is going to be to add sodium borohydride. This isn't a mechanism that we worry very much about, but sodium borohydride will remove this carbon-mercury bond and replace it with a carbon-hydrogen bond so that our final product is this alcohol. Note that this alcohol that we've produced, because we've produced it at a new, we've made a new stereocenter, we would expect this to be a racemic mixture. Let's go back up to here where we made the carbocation. The same idea, the same process is going to occur. Water is now going to attack the carbocation directly, donating a pair of electrons from oxygen into an empty p orbital. Just like we said below, it brings along its proton. It might be running out of space, getting close. It brings along its proton, and just like happened down here, another molecule of water can come in and remove that proton to finish this reaction at the alcohol. Because we have not created a new stereocenter in this reaction, we don't have to indicate a racemic mixture. The two products we make are different, the tertiary alcohol, the secondary alcohol. What was the origin of that difference? Given that both reactions were technically adding water to the alkene, the bottom one using mercury avoids rearrangement by a concerted reaction to form the mercurinium ion.